Hello, welcome to the first video in your flipped classroom Introduction to Calculus series. And we're going to start with limits. It's the foundation of calculus. You might have learned a little bit about limits at the end of your pre-calculus class, but they still might be a little mysterious to you, so we'll try to go slowly. This is the notation for limit. If you want to read this out loud, I would read it as the limit as x approaches c of f of x equals L. And I know there's just a lot of variables here, but the meaning is, well, if you're thinking of a function and you want to know what happens when the input is close to some particular value c, I should say near but not equal to. We'll see why that's important in a little bit. So if the input is near C, what's going to happen to the output? Well, according to this statement, the output will be near L. Okay? You might wonder about this word near. It's a little vague. How near does near mean? Well, there's a precise answer to that question, but I think we're going to talk about that at the very end of the year rather than the very beginning. It's a little bit abstract and a little bit more detailed than we need to worry about right now. But there is a precise meaning to this word near. Okay, so, well, what do you mean? If the input is near C, then won't the output just be near f of c? That's what our pre-calc intuition says, at least, right? Most functions, if you look at the graph, it's some smooth curve. And so if there's a point on the curve at c comma f of c, then when the input is near C, the output should be near f of c, right? That's actually a special case, and it's just because in pre-calculus we usually only study kind of nice, smooth, well-behaved functions. This special case has a name which is called continuous. If this is true, the function is continuous at C, and we're going to talk about that more later. But first, we're going to try and focus on the discontinuous case when that doesn't happen. But first, let's talk about an example that you're more familiar with. You studied rational functions in Algebra 2 and in pre-calculus. And so if I give you a rational function, especially if it's in factored form, you should be able to graph this by hand. Right? Let's remember how to do this. Just a sketch of the graph, right? We don't really care about the scale too much. The main features are important. So if it's factored, it's not quite factored because I have this x squared minus 4 term. This term factors into x minus 2 times x plus 2. Okay? And when you factor this guy, you realize there's a repeated factor in the numerator and denominator. X minus 2 divided by x minus 2 equals 1. Let's cancel those guys out, right? They divide to 1. And so the rational function looks like x plus 1 divided by just x plus 2 times x. And so the zeros of the numerator are zeros of the function. So when x equals minus 1, f of x is 0. That's our root. And when the denominator is 0, we're going to have a vertical asymptote. So when x equals minus 2, or when x is 0, I have a vertical asymptote. So if I'm going to draw this graph, I'll draw features at a time. I'll first maybe draw this dot for the 0 here, then I'll maybe draw the dashed vertical asymptote. I'll recognize the y-axis is an asymptote. And then I'll think about the end behavior when the denominator is higher degree than the numerator, so degree 1 divided by degree 2, I remember that means that the limit as x approaches infinity, oh, I shouldn't use that term yet. I remember the end behavior is that we have a horizontal asymptote at y equals 0, when the denominator is higher degree than the numerator. And if x is a positive number, then the whole function must be positive, so I can start graphing. I know I have a horizontal asymptote, and I'm positive, and I'm approaching 0, and as I get x closer to 0, I have a vertical asymptote. So I'm bounded in the first quadrant there. And then because the degree of this factor is 1, I'm going to change signs. So my vertical asymptote is negative on the other side. And so I start down here, I go through the known 0, I change signs again, and I have a vertical asymptote going to positive infinity here. I change signs again, and I go from the vertical asymptote to the horizontal asymptote. Okay, so that's how we can graph it. So how can we describe some features of this graph using the language of limits? Well, okay, if you want to talk about the 0 of the graph, it's almost kind of using too many words to say too little. The limit as x approaches -1 of f of x equals 0. Well, that's true, but I could have summarized that by just saying f of -1 is 0. And if you know it's a rational function, you already know the same amount of information. Oh, there's one thing I forgot about the graph, though. I forgot that I canceled out these factors. What does it mean when I cancel out these factors? It means although x minus 2 divided by x minus 2 equals 1, most of the time, when x equals 2, well, that's 0 divided by 0. That's undefined. X equals to 2 is not in the domain of the function. So everywhere except for x equals 2, my graph looks good. This little empty circle reminds us that there's a hole in the domain. There's one point does not exist on the graph. Now I can use the language of limits to talk about this. The limit as x approaches 2 of f of x equals the value of this expression when you plug in 2 for x. So I have 2 plus 1 is 3, divided by 4 times 2 is 8. So I have 3/8. So this hole, I can have a hole in the graph at 2, 3/8. In this case, it does not equal to f of 2 because f of 2 doesn't even exist. Okay, this is something for a little bit later in the chapter, but we can think of these numbers c and l as just real numbers, but there is a meaning to the notation when either c or l, or even both, are the infinity symbol. So we can describe the horizontal asymptote at y equals 0 by saying the limit as x approaches infinity of f of x equals 0. As x gets bigger and bigger, you can't really approach infinity because it's not really a number, right? But shorthand, this means as x gets bigger and bigger, f of x gets closer to 0. I can also try to say what happens at the vertical asymptote using the language of limits. As x approaches 0, f of x is getting either bigger without bound or smaller without bound. So maybe I can say f of x equals plus or minus infinity. This is a little bit sloppy. I don't want to say that one limit equals two possibly different things. So a better way to say this might be to say the limit of the absolute value of f is infinity. Now I'm only talking about a positive number anyway. So either it's getting bigger without bound or smaller without bound. But anyway, as x approaches 0, this function becomes unbounded. If you really care about whether the infinity is positive infinity or minus infinity, then you have to break this limit into two cases, approaching from the right or approaching from the left. And that is something we'll talk about more a bit later. Okay, so despite that we have a couple wrinkles in the design, the first way to try to calculate a limit is to just look at a graph of a function or just plug in values into the function and kind of see what happens. It's not a precise way to talk about limits, but it's a good way to get the value for a specific function. So the graphical or the table of values approach, let's just look at one example here. The limit as x approaches 0 of sine x divided by x. This is a mixture of trig function with rational function. Now I claim that the answer is 1, and in order to convince you of that, I'm going to show you two different ways to look at it. Well, I drew this graph on the board, but I can't really do this by hand. I used Desmos.com and I just sketched the graph I saw. You can try the same, or you can use a graphing calculator, but the graph, Desmos doesn't really put this hollow circle here. When you look at the graph on a calculator, you just see a smooth curve. If you try and hover the mouse over the curve, then when you get to x equals 0, it says undefined. But if you zoom in on that point, it's very clear that the curve is passing through the point 0, 1. Passing through even though that one point is not on the graph. So we know 0 is not in the domain, but just looking at the graph, we're pretty sure that if x is near 0, then sine x over x is near 1. If I don't even have a graphing calculator, I maybe just have a regular calculator, I can still do this experiment by hand. I can consider different x values that get closer and closer to 0, and I can just plug that into the calculator and find the value for sine x over x. So I did this. If x is 1/2, the function is already pretty close to 1, 0.959. If I put in 1/10, 0.9983. If I put in 0.01 for x, I'm pretty sure that this is getting close to 1. Okay, so it's not an exact way to calculate. If your limit is not an easily recognized number, like imagine a different function where the limit is square root of 7, I might not recognize the decimal expansion for square root 7. But anyway, I could at least get a decimal approximation for the limit by looking at either a graph or a table of values in the case that a limit exists. In the next short lecture, we'll talk about the case that a limit doesn't exist and how to identify or classify those possibilities.